A very good afternoon to all, and I welcome all to day 3 of your international workshop on introduction to machine learning and deep learning and hands-on experience. And I hope you are all enjoying the last 2 days sessions. Okay, we have given you the complete the session details and everything on your groups, and YouTube link is provided to you. And I welcome your Subraswine sir, and I request sir to start the session. Thank you, sir.
Hello everyone. So we should get started with the day 3 of our workshop on machine learning and deep learning. And I hope my voice is clear. Yeah. Yeah. So yesterday we sort of started with ANN, and we saw that how ANNs can be very much useful for like achieving this for capturing the pattern that there in the data. So I'll spend like first 10-15 minutes doing a recap of what we did yesterday. And yesterday, like while running the code, I mentioned that if you could tweak the network a bit and try to find a better network parameter or network hyperparameter, so that there is a maximum gain in the network performance, you can do that. So if anyone has played around and found a better accuracy than the last accuracy that we discussed yesterday, which was 78.6 or something, they can like ping in the chat. I'll try to see the what is the parameter they found or what is the setting they made. Yeah. So I guess if you play around a bit with the examples and with the network parameters, you can easily find that several ways to improve the accuracy of the system, or you can easily like figure out you can easily figure out which features are important for a classification or uh, uh, a regression problem. So coming with starting with this CNN, we'll start by talking about this. One second. Yeah, we'll start by talking about images. So this will be a bit interesting than yesterday. So let's just like start to talk about images. So first will be recap of the previous session. So what we have learned so far is that we learned that in real life we have to take a lot of decisions, and we have to guess a lot of values, and we have to we're doing so many things, and we want an intelligent machine, if he could do that for us, our life will be very much easier. So so we so with that goal in mind, we started teaching our machines how to predict such something or how to classify something. And yesterday we started discussion with the notion of finding y given x. And we say that if xy pairs are given, and we see that if xy pairs are given and we are given a new x with an unknown y, the way to predict this is to the way to predict this is to take this data and split it into train and test part. This will be train and this will be test. To take this data and split it into train and test part, then train a neural network on this unknown data and test your performance using this one, using this neural network. So and we also understood that this the relationship between x and y is represented by a function fx equals to I. And the thing that we said here, that we need to for to find the value of f at instance 5, we need to find this f of x. And so this is boiling down to like finding a function which is underlying this data, finding a function from the data. And so once we find this function, we can plug this value of x to this function and we get corresponding output for our value. And yesterday someone asked that how to get the function once the neural network is trained, and how do we store it, and how do we use it in the further studies. Yeah, I got a question also first about how to calculate it and calculate a new and b new values by formula, because it's a bit confused. Okay, so we'll discuss that. But so initially, like as I was saying, some people asked that how come so once, let's say we found the function, and so let's say we trained the neural network, and let's say we got a good accuracy of 78, or say 80 or 85, or let's say 90% as well on the test data. So how do we store that, and how do we make a prediction for a new data? So the answer to this question is, so we don't need to so we don't so if you are wondering what is the function here, so the neural network that you trained is the function. Because if you see, neural network is like this, and everything is connected here, and by connection you're meaning that x, you're getting x and you're multiplying it with a W matrix, and you're applying a non-linearity such as sigmoid or ReLU on top of it, and you're getting values in this row. Then you are multiplying this row values with some other weight. So this whole thing is multiplied with some other weight, let's say W1, and again you are applying non-linearity, and this entire thing is your f of x. And when it comes to storing, you just store this neural network, or we just store this model by model dot save function in the PyTorch, where the model will be saved. And when you have a new data of a new x, you just pass this x to model, and it will give you the corresponding y. So in this way we do it programmatically, and but mathematically it is like, if you find these parameters, find this, so this is given, so if you find this w, you just plug the x values to it and to get the corresponding y. But like I would suggest that, like, for now being, since this is a very fast paced or workshop, so just keep it. So just think it in this way, that once you train the model, that model is the model is the function, target function, the approximated function, and you can use this model to store the, you can store this model, and later when you have a new data, you can load this model and pass the x to this model to get the corresponding output. So this is the story behind, like, storing and getting prediction for new data set. And with this story, we then sort of I agreed that uh, so this x and y might not be this simple. This y will be something like class values, male or female, or dead or alive, or cat or dog and bird. And also it can be numerical values such as house price, or you have like uh, let's say stock market forecasting, etc. But this x can grow very complex, and this x can be like uh, a tabular value of, like, say, let's say 10 variables, or it can be an image, or it can be a audio, or this x can be a video as well. So this varying value of x makes the x a bit more complex. So if it is a tabular data, x will be x1 to xn. But today we will see that what will happen, how to, like, deal with this if an x is an image. So we'll talk about today how so is it possible to extract the same in MATLAB NN tool? Yes, MATLAB's NN tool can be used, but since in the recent days, like, everyone sort of use Python, so it was easier for me to refer the same thing in the Python. You can do the same thing in any Turing complete language that is there. The PyTorch NN method gives a lot of functionality, so you don't have to do many things manually. So I'm not sure about MATLAB's NN functionality. They must have, like, implemented this storing and loading the neural network from scratch. Okay, so I got another question. Is that I got another question uh, from Yatin, that also a fast recap about how to calculate A new and B new. So Yatin, if you remember yesterday's class, we let me go to the notebook that I opened yesterday, day 2. So the calculation and all, I can make it more clear, but since, like, so I'll share something to for you to read, but about the calculation, so I have to do it from the scratch. So I'll find some time to do that. But if you look at this code that we did yesterday, the calculating the new A and new B is achieved by these two lines, and it is same for any neural network that you develop, even if today also. You just do loss dot backward and optimizer dot step. So this loss dot backward will propagate the loss to the into the neural network, and this optimizer dot step will update the value of A and B. Like, A new will be A new, A old minus the d by dl by da into alpha. So the formula that I wrote is integrated inside this function. So for the time being, so if you couldn't understand yesterday how those things are derived, so you can just remember that, okay, so somehow I need to get a new A, and that new A should be good enough to make my loss even lower than the previous epoch, and this is achieved by this functionality. And if you want exact derivation, the derivation for that will change for different loss function as well as different network architectures. So for the simplest one, I'll give you a derivation in some time, but the idea is this. Yeah, give me 1 minute. Okay. Then we should, I guess everyone's doubts are clear from yesterday, before proceeding on today's topic, that is CNN. So before starting with CNN, let's just understand how images work. So images can be of two types. One is grayscale and one is colored. So if the image is grayscale, let's say an image of fish is there. Let's say image of cat. Okay, so this is the image of cat, and if you see a black and white image of cat, it's very high. It's very high chance that this image will not be of much larger resolution. And by resolution, okay, so I'll start talking about resolution. So by resolution, you must have learned about this 720 pixel image or 1080 pixel image or 4K image. So if the value is 720 pixels, so it says that there are 720 pixels in this row, and similarly by adjusting the aspect ratios, there will be similar number of pixels in the column as in this vertical direction as well. So what is a pixel? So pixel is something that denotes, pixel is the smallest representation unit in an image that denotes the intensity of light. So for a black and white image, if it is 0, then it is white. If it is black, it is 255. And any value in between will be some intermediate color. So here it will be a bit more less white, and it is here it will be a bit more darker. Here it will be something like that, and the end 255 fifth one will be the darkest. And everything has value associated with it. This you can call this 57 and so on. And this will be 254. Okay. So, so you can say in every image now is a combination. So any point, if you zoom in to an image at any point, you can see one of these 0 to 255 values. So all this, so this entire image is if you see an image, value will vary from in any pixel ij will vary from 0 to 255. So this is the black and white image. So when you say 4K, so that means there are 4,000 pixels in this direction. And when you say a colored images, so colored images has 3 channels. One is red, and the second one is green, third one is blue. So when you see color images, here again also you have pixels. You have pixels, and this pixel value will vary from again 0 to 255, and the value of 0 means white, and value of 255 means the darkest blue or darkest green, darkest red, and say and this intermediate values are just lighter version of that. So it varies from 0 to 255 in all three cases. So when you see a color, it's just a linear combination of this red, green, or blue. When you see pure blue, then that person is that in that region, the red pixel and the green pixel is at 0. It's just white. So when you mix white with blue, it will again blue, and it will be like transparent. And so every red and green will be cancelled out, and you can only see the blue. If you are seeing say yellow, then if you're saying say orange, then you must be seeing some red and some green. So it will be like if you see a picture, if you see this corresponding picture of this at this point, and if it is red, that means it has so if it is orange, it is 80 percentage of red plus 15 percentage of green plus 5 percentage of blue. So this is the way we represent the colored images. So enough about the images. So let's just talk about, like, how to process these images. So how to process these images? So first, so let's just, like, let's just start with the task of classifying digits. So there is a popular data set that is called MNIST, and this data set, we have to classify handwritten digits into its corresponding digit. If it is written 0, its label will be 0, and if it is written 1, its label will be 1. So so while framing a classification neural network for this, so you should know that these are images, and these are not like manual tabular data where you have say x1 to xn, where you can just feed that to a neural network and get your prediction at the end. So uh, so so here the story will be different. But apart from that, let's say, so you have to find a way to insert an image to a neural network. And so this thing we have to figure out how to insert an image to a neural network, because image is not like the tabular data that we saw earlier. So if someone can, like, tell in the chat, so since we are doing this digit classification, where where the that in the data set we have, so x is the image here, x is the image, and y is the label, as a level. And if can someone tell me, like, if i if i if I design a neural network for this, and let's say I figured out how to input image to the neural network, so what will be the number of output neurons? Like, so there will be some in input neurons, there will be some hidden neurons. You can attach as many hidden layer as you can, and as many hidden unit as you can, and there will be some hidden neurons. I put 3 hidden layer, and there will be output layer. So can someone tell what is the number of neurons should be there for this task, where we are trying to classifying digits from 0 to 9? So what is the number of neurons in this output layer? Yeah, I got an answer 10. Yes. So it will depend upon the number of classes that you have in hand. Since there is 10 classes, the number of neurons at the output layer will be 10. So please repeat it once again. Yeah, I'll do that. So remember yesterday when I told about when we're classifying if the passenger is dead or alive, what we needed, that we needed a probability score for dead and or for alive. So to get a so we cannot, so the network will not output a discrete number that okay, this is dead and this is alive. But the network at the end, what it will do is that it will give a probability score that will vary between 0 to 1. If and you have to get to pick a threshold, which is generally picked as 0.5. If it is more than 0.5, then it is dead. If it is less than 0.5, then it is alive. So to do a binary classification, we just need one cell at the end. But let's say we are doing a task, we are classifying a task where the goal is that if the person is dead or alive or injured severely. So now there are three classes. Since now there are three classes, it is crucial to now figure out what is this dead. So it is crucial to figure out what should be the probability that should be assigned for dead, alive, or injured. So now you need three cells in the output layer. Now you need three cells in the output layer, which task. Okay, so now you need three cells in the output layer, and this will this everything. So all these three layer will correspond to something. One first, let's say first will be correspond to dead, second will be alive, and third will be injured. And you will assign some probability score, which will vary between 0 to 1, 0 to 1, 0 to 1 to all these three things, and as well as the probability score of A plus the probability score of T plus the probability score of P should be equals to 1, because as you know, the probability score of all the events should sum to 1, so that's why it should sum to 1. So similarly, here we are doing a classification of images, digit images, which varies from 0 up to 9, and to, so let's say I put all these things into the network, and the output is like so in the output layer I need 10 cells where the first will correspond to 0 and second will 1, and similarly the last one will correspond to 9. And if you add probability of 0 plus probability of 1 plus up to probability of 9, you will get 1. So this is why the number of layers in the output layer is 10. I hope you get that. And moving forward with our discussion, we'll now think about moving forward with our discussion. Now we can now think about uh, how to import these images as an input. So anyone got any ideas like how should we import these images to the network? The highest probability score of neuron is considered in case of 3 neurons at least at output. Yes, in case of 3 neurons or n neurons, the class assigned to the uh, to the uh, to the task will be the highest probability that is achieved by the corresponding neuron. If the fourth number, if the second number probability is highest, we'll assign that as the class, predicted class. Okay. Coming back to like how should we sort of uh, assign coming back to how should we sort of assign images to the network. So so yesterday, if you remember, I discussed about tensors. I said that this is an array or one-day tensor, and this is a matrix or a 2D tensor. Similarly, you can grow this to make 3D tensor as well, if you like. This is like 3D tensor or 3D matrix also we say sometimes in mathematics. So if you look clearly, if there is an image is there of something, some scenario or something, and each pixel is a value between 0 to 255, and if you put this image in a matrix format, so you can get that. So let's say the size of image is n, you'll get a n cross n matrix. So it is safe to say that an image is a n cross n matrix. You can store an image as an n cross n matrix. So this is for grayscale image, and when you move to a colorful image, you can store that as a 3D matrix of say n cross n cross 3. Why n cross n cross 3? Because n and n will be the height and width, and 3 will be the depth. And here the depth is 3 because an image is of red, green, and blue. So here image is a n cross 3 matrix. I hope this clears this is clear to everyone that image can be sort of represented as a matrix and 2D and 3D matrix. Then coming back to the feeding these to the neural network, I'll start by 1 second. Give me 1 second. Uh, yeah. So we now saw that okay, this is the way we can see the say an image, but how should we feed the same to the neural network? So when we start talking about feeding this thing to the neural network, the first idea that that came to people mind earlier is that let's just stretch it. So let's say you have a 3x3 image of values 1, 2, 3, 7, 9, 8, 12, 2, 4. So instead of you will see MNIST is a 28 cross 28 image data. So this is 28 cross 28, which comes around 784. So when you see this matrix, uh, so so what you need to, so what people did first is that, let's say this is a 3x3 image. What they did is that they just flattened it. They flattened it, and by flattening, what they did is that they just made a array out of it, or 1D tensor out of it, which is like 1 2 3 7 9 8 12 2 4. If you recall, now this is similar to x1 x2 up to xn, and up to xn, and this can now be easily fed to a neural network. This can now be easily fed to a neural network. And since we have like 10 classes, the output will be 10 units, and you can get the prediction out of it. So yeah, so let's say we're looking at this handwritten digit from 0 to 9, and its size is 28 cross 28, and if you flatten it, so you can get a so if you flatten it, let's just do it in the yeah, flatten it, will get a long vector, and this vector will be x1 x2 up to x784, and you connect other layers to this network, and finally you put 10 neurons at the end to achieve to do this classification task. So here the input layer will have 784 dimension, and the hidden layer, let's say 100 or 1000, 100, and output layer is 10. So if you say, this is pretty simple, where you're just taking the image and then you're flattening it, and then you are putting it to the neural network to calculate the prediction scores, and accordingly you train them. So this is the way, like, in the initial days, people started processing the images, and getting meaningful results out of it, like classification or prediction, or things like that. So now I'll take a pause, and I'll ask that. So I'll ask two things. Okay. Now I'll take a pause, and I'll ask. So do you find? Is there anything till now that I have discussed is not understood by you? So if you couldn't get anything, now you can ask me in the chat itself. I got two questions. Okay. So, what may be the needed hidden layers, and how can we decide the number of hidden layers for this network? Great. So, so what happens is that nowadays, so the task that you will be evaluating, uh, so there are some standard tasks like this MNIST, and there is Cipher 10, and then there is face dataset, then there is road sign dataset, and people have already like done so much amount of work. So you can just pick one architecture, and then you can sort of copy the architecture and use it. But what will happen if you're starting to sort of if you're starting to sort of creating a own data set and trying to train your own ML model on top of it? So one way to go about this is that, so there are some schemes which sort of says you scale down if the input dimension is say 1,000, so then you can go down to, let's say, half, half, like that. Like if the initial is the 1,000, then you come down to 500. Second hidden layer, the third hidden layer will be 250, and fourth hidden layer will be like 168, sorry, 125, like that. And when you come close to the number of classes that you have in your hand, then you can just put the output layer after that. So that is one way to go about that. Second way is the experimentation, because the number of layer and number of neurons in a layer is again a hyperparameter, and you have to decide on your own by experimenting how uh, like how much hidden layer and how much neurons per layer will work for you. So this is purely experimental based, and for this I'll try to show you how by changing how the number of hidden layers will play a crucial role. So that's why yesterday I was forcing that you should play around with the neural network that I developed yesterday, and you should see that how the number of hidden layers and neurons per hidden layer is affecting the accuracy, test accuracy, uh, 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 will affect the accuracy and test accuracy of the data set. Next question is that, so I guess Jatin, your question is clear. Next question that I get is that how to update a trained neural network model. Okay, so when we do, so this is a out of the topic question, but I'll address that. When you train a neural network, so there are two modes of training a neural network. So a model, so in a PyTorch model, a PyTorch model stays in two forms, one in train mode and one in evaluation mode. So when you operate the model in the train mode, what it does is that when you do the forward passing, it the keeps track of the gradient and keep all this information about the gradients for the future. So it will say that if there is a back propagation in the future, I will save this thing with me. So that is on the train mode. And when your training is done, what people do is that they turn off the train mode and turn on the evaluation mode. So they just transfer the train mode model in the train mode to the model to a model in the evaluation mode. And by doing that, now you have frozen the weights. So the A and B's that I discussed yesterday, the A and B's are the weights, or what we can say the parameters, are now freezed. It will not change. So now you can make prediction on top of that. So if you want to train again the neural network, what you can do is that you can take the model and then just make it change the mode from evaluation to train. And in the train mode, if you train it again, it will be trained again. So if I go to the code that I wrote yesterday, if I go to the code that I wrote yesterday, you can see that when we when we defined the model and created the model object, the model is in the train mode by default. So we don't need to put it in the train mode. So what we did is that we take this model, we pass this extrain, and while we pass this extrain, it is sort of uh, um, keeping track of the calculation so that in the backward step, it can calculate the gradients for you. But when you did the evaluation of the trend model, we put it inside the torch.nograd block. So this what this block will do is that this block will prevent the model to calculate the gradients, because we do back propagation only in the training part. We do not do back propagation while evaluating. While evaluating, it's just a function. It's just a function that consists of parameters and inputs. And when you give your input, it will give you the result. So one other way of going about this is that doing the changing the model's mode from train to eval. So model dot eval. So when you if you want to make training again, so you have to do model dot train, and using that, after this point, you can train your model. So this is about model training and all the questions that you have asked. I guess the question is clear, Dr. S. Chandramouli. So now, like, we'll start uh, we'll start discussing about so yeah. So one question like so what is the problem that you see in this method? So uh, so I had an image, and you can say image is a two by two sorry uh, two cross two sorry two-dimensional n cross n image, or for an 3D image, sorry, colored image, it is a 3D tensor of n cross 3. And what I do is that I just flatten them, and I'll get an array, and I can just pass those values to the neural network to get the predictions. So this is a pretty simple way of dealing with it. And if someone could, if you could like point out a problem with this method, I'll be more than happy. So what is the problem with this method? Why we shouldn't proceed with this? Please type it in the chat. Instances, maybe dimensionality. Second is maybe while flattening the obtained matrix can be lengthy as 784 earlier. Okay, so I both this answer are correct and same. So apart from that, there is also another problem that you can face while flattening and using image like this. So I'll okay. So apart from that, one second, yeah. So apart from that, like, can anyone say, like, what is this way of flattening? Why this way of flattening is not a very nice way of dealing with things? Okay. So I'll start with explaining, like, why this is not a good idea to go about. The first thing is the dimensionality.
নিচে ফ্রেম হচ্ছে নাকি এগুলো কি হবে ব্যাপক কাট পেয়েছে তো কে নিয়েছে বেশ সুন্দর পুরোনো একদম সেফ
Sir, please everyone mute yourself.
So the first one is dimensionality. Okay. So when you look at images, yeah. So when you look at images, so this is the handwritten digit is 784 dimensional. That is 28 cross 28, which is I guess fine, because 784 is not that like big of a number. It is still big because if you see, the input layer size will be 784, and even if you place someone around 200 hidden layer, the matrix that you will be getting for the weight that to connect these two layer will be 784 times 200, which is huge. I agree, but still, like, since our computers are big now, we can evaluate these things pretty easily. But so now you see, all your images are either HD or full HD. So that is, if you take a square HD image, there is 1080 pixels in this side, and also 1080 pixels on this side. And if you multiply that, so let's say you multiply 1000 cross 1000, it will be 10 to the power 6, which is huge for a neural network. And if you see, the input dimension will be 10 to the power 6. Even if you put 1000 layer hidden layer, the matrix that will be getting will be like cross 1000. So which is impractical. We cannot calculate that, and we cannot. The matrix will be very large. So that is the number of reason number one why you should not flatten it. Then the reason number two why you shouldn't flatten it is the spatial relation. Okay. Spatial relation. By spatial relation, I mean that, so when you make a prediction, when you are making a classification, when you are working on a classification task, Yeah. So when you're making when you're doing a classification task or when you're doing a prediction task, uh, there is high possibility that you care about what are the variables that you are putting as an input, because the variable that you are putting as an input should contribute to the decision that you are taking by putting in that as an input. So what I meant is that, let's say you are trying to predict survive or dead, and and you also so when you're trying to predict the things that if the person is survived or dead, uh, so what are the things that you think would contribute while making a decision? So you see, gender is a very crucial plays a very crucial role while deciding if the person is dead or alive, because if it is a woman, there is high likelihood that she must have survived, because women and children were allowed first to go out of the boat. uh, so uh, so when you see all these things, so when you think about all these things, the decision that you took, or the decision this neural network takes, is highly dependent on the input that you are providing it. So in case of images, so images are so in case of images, you are providing input as images. But let's say you are predicting the cat, and for predicting it, you sort of passed the cat image and you sort of flatten it. And when you flatten it, so it just took the first row of all the pixels and put it here. Then it picked second row, then it put it here, and so on till the last row of the pixels. So what happens here is that, let's say uh, the eyes that is above this its fur, or above its this mustache, is meaningful. But if you when you flatten it, and if you flatten this row, his eyes will come somewhere here, and it's this mustache will come somewhere here. So this evades. So this is making this semantically not meaningful. So eye is just above the mustache of the cat is a meaningful semantics. But if you flatten it, the entire image will fall in some area of the this long array, and the entire relationship between inter feature relationship between all these things will be hampered. And in that way, it will not be a good way of learning things, because if you are trying to teach a machine that this is a cat, so it should see the cat as it is. It's not like that, because if tomorrow you put a image of some other animal which has eye here and has some fur on top of his hair, and the machine also for this will put eye somewhere and fur somewhere, and it will think that since there is eye and fur in this amount of distance, it is a cat, and which is wrong. It is not a cat. So I guess you got my point. So why we should not flatten this when we come across images. So is this thing clear? Like, why spatial relationships matter in the context of images, and why we should not hamper the semantics of this by just flattening it. Put in the chat like if you understood or something, because these are crucial things to understand, and it's harder to proceed without it. Yeah, great. So so now what should we do? So since we cannot flatten it and we cannot feed it directly, So what is the next step that we can do? Uh, um, the next step that we can do to like prevent this. Jatin saying, sir, explain again, please. Jatin, just okay. So I just explained this briefly. So what I was telling is that if there is an image and you want to put it into the neural network, so one way is that you just take and flatten it and pass the flattened image to the neural network. But the one problem is that dimensionality. Once you grow in the image in the dimension, the input dimension will be very huge, and it is very hard for computer to remember this big of a matrix and do computation on top of it. And second problem is the spatial correlation. So when you speak about uh, spatial correlation, we sort of agree that if an image what we are seeing, we're identifying it as a cat just because its pixels are arranged in that way. Like the pixel that correspond to the mustache of the cat is near the pixel that is correspond to its eye and its nose and its tongue. So if you flatten it, the positioning of the relative position of this positioning of this filter, this pixel will change, and its its fur will lie somewhere here and its eye will lie somewhere here, and it will be very difficult for the it will be very difficult for the um, machine to understand why this is so why this should be a cat. So that's why we do not so that's why we sort of don't flatten it when it comes to images and complex images. The next question comes like, what should we do, what should we to do to prevent this from happening, because we cannot uh, sort of expand it because it is too big, and we sort of cannot like play around with this yeah, we sort of cannot play around with this with direct image, because direct image we cannot import it to the neural network. So what you think we should do in this case? So the solution is an interesting and is very interesting, and this gave rise to the creation of CNNs, which is also called convolutional neural network. Okay. Okay. So give me 1 second. Okay. So what should we do? So the problem we had is that we cannot flatten it because it is large. Also, we need to maintain the spatial correlation between the pixels in the image. So if we could do this thing, if we could, so let's say there is a big image. So if so, and this its size is 1,000 cross 1,000. Let's not put any size to that. Let's just say n cross n. And if we somehow convert this image to M cross N, sorry, M cross M, such that N is M is much lesser than N. That is condition number 1. And condition number 2 is that, and so let's say this is image I and is image I dash, and I dash should be giving us the same visual appearance as I. So when you see this, like, you're sort of creating a smaller image version of the bigger image, such that the smaller image has all the features that you have in bigger image, and it is much smaller. And if you do flatten of this, the size of the flatten will be M cross M, which is much smaller than N cross M. So if we can do that, then we can pass this thing to the neural network and get our prediction Y. So I guess this is clear to everyone. I mean, so this is clear that how. So I guess this is clear. I guess this is clear why we should. So what we need. So the need is now clear, that we need a converter that will convert this input image to IDAS, where the input image size is N cross N and the output image size will be M cross M. Okay. So to convert this image of M cross N to M cross N, there are a couple of steps that we perform. So I'll do the and the net. So we also train a network to do it, and that network is called convolutional neural network, and we apply convolution to shorten the image, or let's say minimizing the image to a smaller resolution while maintaining all the features that the image possesses. So that is CNN, in other words, convolutional neural network. Okay. So let's start with CNN, and so the input to the CNN will be an image. The input to the CNN will be an image. Let's say the image of N7. And let's say we have an image of N7 and we sort of pass that to CNN. So let's say this is my CNN. In the output, it will give me a 7, but small 7. Some representation of the 7 which still looks like 7, but it is much smaller. Let's say if it is 28 cross 28, I'll get so let's say 8 cross 8, which is 64. And if I flatten this, I'll get something like this, which is 64 dimensional. Then I can connect that same to another hidden layer, let's say 32, and then I can put the final layer of size 10 to do the prediction. So let's learn about how this CNN work and how this CNN sort of transfer this bigger 7 to smaller 7. So CNN consists of generally 3 layers. So those are, so I'll now explain layers of CNN. Layers of CNN. So the first layer is called convolution layer. So when you discuss about convolution layer, a convolution layer is pretty simple actually. So it performs a convolution operation on the input image. So let's say your image is 7 plus 7, sorry, 28 plus 28, and you'll be requiring. So if you send this to a convolution layer, you'll be getting an image which will look like 7, but its dimension will be reduced, the height and width. So before starting with convolution layer, let's just learn about like what is something called a filter or kernel. Or kernel. So earlier, what people used to do is that uh, they what people used to do is that they used to sort of yeah. So what people used to do is that they used to sort of take image. So you must have done this recently also. They used to take the image and they used to sharpen it. If you see all your image editing apps, they have this feature of sharpen the image or blur the image or sort of find edges from an image or increase contrast, whites, etc. So, what if I tell you all these things is just a result of a matrix operation that is called convolution. So if you want to sharpen an image, so you need to find the sharpen filter. Let's name it FS. So once you find the sharpen filter, you need to convolve it around the image. So you need to put it here and get some results. They need to put it here, get some results, and in this way you can build your new image. So I'll go detail in it. So I'll exactly show you how you sort of can do this and get a good sharpening of your images by numerically doing this here. Let's say your image is a 5x5 image, and you have this value, say 2, 7, 9, 0, 1, 6. These are all pixel values, so you don't need to worry about like what is this value there. So let's say they are this pixel values. I'm assuming that so let's say this is an image, and this is a 6x6 image, and you wanted to sharpen it. So what will you do is that you will take a sharpen filter. Let's say the filter dimension is 3x3, and it has values like -1. Let's say the middle one is 9, or let's just the filter. The middle value is 4, and -1, -1, 0, 0, 0, and 0. This is 9. Make it 7. Yeah. So when you pass, how to use this filter? So what you will do is that you'll put this filter on this 3 cross 3 block. So everything will be 0. This top 4 will be 0 when you multiply this with this, and all these 4 will be -1, and this will be 21. So the resultant value that you will get will be -7 plus -7 plus -2 plus -1 plus 21, because 7 into 3 will be 21. So that will be like -14 minus 3 minus 17 plus 21, that will be 4. So the corresponding values in the output will be 4. Similarly, you will move this filter one step to the right, and you will do this exact same thing for this. And let's say you get another value 7 for this location. Similarly, if you move, you will get second value, this will be third value, fourth value, till fourth value you will get. So let's say third and fourth value are 2 and 7. And after that, what you will do is that you will shift one block down, and you will calculate the same thing for this block as well. Let's say you're getting 9 from this block, and if you start sliding right, then you will get the corresponding value 10, 1, 7. And 7, and you keep sliding down, you will get one value for here, one value for here. That's it. So if you fill it out, if I fill it out randomly, it will be 4, 9, 13, 91, 21, 47, 62. If you see clearly, now this 6 cross 6 image is converted to 4 cross 4, and its size has reduced. But since we took a sharpen filter and just applied on top of it, we just got a sharpen image in a smaller dimension without affecting the quality of the image. So this operation is called convolution operation, and by doing this operation once, doing the operation one after another for several times, you will sort of be getting very smaller images as compared to the input image. Can we get recording of your lecture also by end of each class to refresh? I guess I am sharing the recording and everything to so I guess ma'am is doing this live on YouTube, and if you contact her, she will give you the link of this lecture. Anyway, so Yeah, so I was talking about this. So I was talking about this uh, uh, this feature where I was talking about this feature where you sort of get smaller images out of the larger images, and this is called convolution layer. And so in the convolution layer, uh, so in CNNs, so we don't actually apply filters by hand crafting them, because the sharpen filter and blur filter might be useful for some tasks but might not be useful for all the tasks. So what we do is that instead of handcrafting these features, we allow the neural network to learn it. So we now I can say that now I can say that let's say this is the image and I need a filter F such that if I apply this filter to this image, it will be reduced and it will give me correct representation of the previous image, which is reduced and correct representation of the of original image, such that this representation will help me getting the classification job done in a better way. So so what we do is that, so you remember the W, the weights will go here. So these are the weights now. So so when you will update, so this is fixed because this is input. So when you will update the weights or your A's and B's, so these will be updated, and with time the model will find the most appropriate filter for your image, such that the underlying task will be done very efficiently and the loss will be very minimized and you will get better accuracy. So here the problem is that instead of finding weights in the neural network, which you will do in after the flatten layer, but here now you are like searching for filters which will reduce the images. So if you are able to find these filters, so what they say is that you don't just find one filter, you can sort of find n filters, and each filter will give you the corresponding image, transformed image, which will be much smaller than the original image. And you can club these images into a 3D image, and its channel will now no longer be 3. It will be somewhere around n cross m, and this will be a 3D image which sort of smaller in size, as well as it is sort of a correct representation of the this image. And if this is again large enough for you, you can again do the same thing. You can again take filter, and now the filter will be 3D because our image is 3D now. Now you can just take this filter, several filters, and again all these filters will be learned, and you can use this filter to get corresponding again 2D images. Then you can again club these images to get a 3D image, which will be smaller. So you see, you are growing in the height side, but you are reducing very fast in the width and height. So you're growing the depth side, but you are reducing in the front of height and depth. So let's say after some iteration, you are very the image is now very small enough, but it has a bigger depth now, but the height and width is very small enough. Now you can flatten it to a better. Now you can flatten it to a more practical size which can be fed to a neural network. So all the part that is apart ahead of this is called neural network, and all the part that comes from here is called CNN or convolutional neural network. Go still here. So these details, so it will take some time to grasp, but the, 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 the basic fundamental thing behind that is that you're taking an image, you're assuming, you're guessing a filter, and you're learning this filter with time, and you're sort of passing this filter to get smaller representation, and you're clubbing this together to get a 3D image, and you're again applying this filter to get 2D images, then you're again clubbing this, and then you're again doing this till you get a small enough image to flatten and put it to the neural network. Is M depth equals to the number of filter used? Yes. So when you get input image, so when you get input image, it has a size of n cross 3. So when you apply filter number 1 to it, you got an image of n cross n. When you apply filter number 2, so let's say 1 1 1 2, you get another n cross n. Up to when you apply filter 1n, let's say k, you get another image of size n cross n. And when you club all these things, you'll get an image of n cross k, right? And you have n cross k. Now you will apply filter 2 1, and you will again get n cross n. Filter 2 2, you will again get n cross n. Similarly, you will again apply filter 2k, and it is n cross n. Then again, it might be k or it might be r. The number of filters in this layer should not be equal to this layer. It can be larger. So generally, r is larger than k. And you club all these things, and you will get another image of n cross r. So just imagine it in that way, like we're getting a bigger cubical image instead of getting like 2D image. And so when you sort of work with these images, you can see that this filter size. So this filter size, if you see the filter size, so here the filter size is let's say L cross L, L cross 3, because now your image is 3. So for a 2D image, you should fit like this. If the image is n cross n, your filter will also be L cross L, because both 2D. If you have a 3D image like this, with the R, red, green, and blue, your filter should also be 3D, right? Like this. So your filter in this case will be L cross 3. But what is the size of filter here? The size of filter here will be same as the size of dimension of this. The size of filter here will be n cross, sorry, not n, because since we are working with the filter, it should be some L cross k. Because if this size is k, this size should also be k. And this is n, but this can be L and L. So I hope this part is clear, how we are applying convolution and why we should care about convolution, and why it is getting the images reduced to a certain space. Is everyone clear what I was trying to say for the past 30 minutes? Put in the chat. Can you repeat once again, sir? So which part you want to get repeat? Like which, where did you stuck? Like what, ask me the exact question. Like where did you did not find it very understanding from these steps? Or you're completely lost? Okay. Yeah. So there you need so sort of here you need uh, yeah, here so one crucial step is just convolution. Apart from that, we apply uh, uh, two more things as well. That is pooling and there's something called ReLU. So we discussed about ReLU yesterday, the ReLU layer, but I'll discuss about pooling and I'll see like I'll show you how pooling is useful in this context. Before going to the pooling layer, so I should like let you know about like why do we need pooling in the first place? Uh, we have convolution, but convolution help us reducing the size, but as well as it sort of increase the depth level as well, and also uh, in pooling we sort of in pooling we'll sort of try to emphasize certain region of the image and we'll try to de-emphasize some other reason, the unimportant reason of the image. So let's just start with the next layer that we'll talk about. Next layer is pooling. Yeah. Give me 1 second. So let's say you have an image and you applied convolution layer to it, then you got a smaller image. So then what you do is that you apply pooling layer to again shorten it, also highlight places where there is important factor. So how we go about pooling? Pooling is very simple. Like pooling is either you have either max pooling or you have min pooling. You don't have min pooling, I guess. You have average pooling. So what happens is that, so in pooling you don't have any filters, so you don't need any learnable layers now, so you don't need NW. So so in convolution you need parameters to sort of deciding which sort of like sorting the image to a smaller value. In pooling you don't need that, and here you, without using any parameters, you can again reduce the image. So what pooling does is that it just take this as it just take this any block. The pooling block will be like 3x3. It just calculate the maximum, find the maximum out of it, and sort of put it out in the next image. So if you transfer this to right, shift this to right, so then it again consider then this 9 pixels and find the maximum and place it here. So for example, if you take this into account, and apply pooling on top of it with a size of 2x2, you can easily figure out that you take this 2x2 block and then the maximum is 10. Then again you do a shifting, again maximum is 10. Here you do again a shifting, the maximum is 7. Similarly, if you shift a block below, the maximum is 10, and again it is 41, 47, and it is 13, 91 is 91, and 91. So you just like taking a safe and taking the maximum out of it, and its size will be 3x3. You see a reduction in size, but you just took the maximum in a local neighborhood, and by taking that you'll still get a valid image which will look like the previous image, or even if it is not looking like in to a human eye, it will be it will have the same number of features or similar features as an same number of features as a human as a as the previous image. So that features can be used to classify things. So talking about all these things and applying ReLU and pull, so you can also do a average pull. You can take the average of this 4, which will be 19, 9 plus 10, 19 plus 4, 23 plus 7, 30 by 4. which is 8.5, I guess. Yeah, 8.5. So this value could be 8.5 in the average pool. The average pooling. Okay, great. So this average pooling, this average. So if we so average pooling and max pooling is done, so you sort of get a smaller representation of the image without any parameter by just taking averages and max. This part is done. Convolution is done. This pooling is done. Next third thing is value. So why do we need ReLU in an CNN? Yeah, so why do we need ReLU? Because you know that in images, the value lies between 0 to 255. All the pixels that you see will lies between 0 to 255. But when you sort of do convolution operation, specifically convolution operation, what happens is that you sort of ending up like creating some negative values, right? You sort of end up like creating some negative values, and as you know, negative values are not welcome in the images. Also, uh, to resolve that, we apply ReLU. So as you know, ReLU is maximum of 0 and x. That means if a value is negative, it will be 0, and if a value is positive, it will kept as it is. So this is the story behind ReLU. So we apply ReLU to cancel out all the negative values, as well as I discussed earlier yesterday, ReLU is a beautiful activation function, and is a good and a very popular activation function that we use for the to provide non-linearity in the neural network. As you know, all the tasks that we see in real life is non-linear. We cannot rely upon linear combination of input features to get the output feature. So this concludes what are the things that we sort of care about while creating a CNN. Yeah. But apart from that, I'll discuss two major problem, to not one major problem and its solution while doing the convolution. So further, I'll take a short example. It will be very short. So let's say these cubes sort of represent pixels, and we are sort of doing convolution around it. So when you pass a filter here, you get a value. Then you shift this filter, you get the corresponding value again. But if you see, if I erase all these things, if you see this number, it is involved in this block, this block, this block, this fourth block, fifth block, sixth block, seventh block, eighth block, and ninth block. So while calculating the stuff for all these blocks, all these 9 blocks around it, this pixel is involved. Similarly, every pixel is involved at least 9 times when you are at most 9 times when you are evaluating the corresponding convoluted image. But if you mark these border neurons properly, they are not part of many computations. So if you see this first neuron, it is just a part of one computation, and these are only part of maximum of three computations. So these are part of maximum of three computations. So as these ones, three computations, and so are these ones, three computations. So it is very trivial to say that those are not getting participated in the computation. So it is very safe to say that the features that lies in the border are not reflected enough in the resultant image. But to make a prediction, we need strong signal from all the features and strong appearance of all the features to make a decision. So to do that, we do something called padding, zero padding. As you know, zero is representation for white, and zero is representation for white, and we sort of uh, uh, put zero for white. So what we do is that you around the images we put a white patch, just like binding a photo. We put a white patch so that when you do pooling and convolution, we sort of include everything, and these neurons are not the border ones now. So this will be included at least 9 times now, and these white are included 3 times. Since we don't care about this white because that doesn't contain any features, we are happy to say that this our border level feature are given well importance and they are involved in the computation. But when you look at so this is a theory behind zero padding. And there is also a notion of stride that we say. Stride is that so when you are doing computation, so if you are this initial block, if a second block is just shifting by one, that is called stride of one. So if tomorrow someone comes and here is its image, and here is the first filter, while doing the second filter, instead of starting from here, he start one block away, and here now the stride is 2 because it is skipping 2 block. So it is just going to the it is skipping 1 block and going to the second block that they find. That's why the stride is 2. So there is a nice formula as well, given the input image of size n cross n and stride as S and padding as P and the size of kernel as K cross K. What will be the output image size? So it's a homework, like you figure out what will be the output image size given the input image is n cross, let's say n cross m. N cross n is fine. N cross n is fine. Okay, so this is, I guess, the end of 2 hours now, and we have 1 more hour left, and we'll be focusing that 1 hour on doing the hands-on. And before starting that, I'll be sharing the hands-on set with you, and you guys will be sort of if you want, you can follow along with me. So we'll take a quick 10 minutes break, and we'll resume after that. I'll be sharing this day 3 notebook with you all guys, and you can follow along with me in the code. I'll share it now, and and everyone please respond if you can access this notebook and sort of run it. There, I put it in the chat now. Just let me know in the chat if you can access this or not. So I hope everyone is able to access the notebook, and we'll start with our code. And this will take a while today because uh, 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 that network has grown and the data size is bigger, so we sort of need time to run it, and I'll also you a trick how to run it efficiently. So before starting, give me 1 second, I'll just plot and so uh, the images. So yeah, so what we are doing today is that we'll be working with this MNIST data. So as I said, MNIST is a data set of of- 1 second, my code is throwing error. This should be able to. So give me 1 second. Nope. Oh, I hope this works. No, I'm not able to show you, but yeah. So if you type MNIST, if you type MNIST in the net, you can see these little pictures where this MNIST dataset is a dataset of handwritten digits where the input is written digits of hand by hand, and the output is the corresponding level. Suppose is one, and the output is one in digit, and the task is to given this digits as input, and you have to predict what is it written in the text as numbers. So the task came when people started to automate reading the addresses. So if the address is written in, let's say, digits, um, uh, 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 if the address is written in handwritten digits, so the task was to capture that to capture those addresses in camera and sort of figuring out what address is that in digits. So this was a very standard data set back then, and also a standard data set now as well. People still use this data set, and if you want to learn more about this data set, you can go to the website and check. So we'll be working with that data set, and unfortunately I couldn't show you in the plot, but yeah. So to do that, so remember as I told previously before some time, we can do it in two ways. We can either put pass the image to a convolutional neural network, or or we can pass the image to a artificial neural network, where we have to stretch the image into 784 dimension. So I guess you must be clear on that. So as like yesterday, let's import everything. Like torch is here, and torch.nn is here, and we have optimizer, and we have and for the data sets, we are specifically using a new library today that is called Torch Vision. Torch Vision is a library that contains all the image data, and there is also a library that is called Torch Audio that contains all the audio data, and so on. So Torch Vision, that's a torch. It's a it's a part of Torch ecosystem where it speaks about you have and you can use this library to get the dataset and transformation that you need to perform on the data set. And as I discussed yesterday, so you can see, so this code is well commented, so you can actually read the code as it is. We are defining an ANN model by defining a ANN class, and this would be a child class of NN.module. It's just like, formal, and it will be same for everything else, so you don't need to worry about that. And here we will define the network here. So the network that I'm defining now is that NN.linear. So linear layer is a representation of that ANN layers. So NN.linear is that, and the input layer is of dimension 784, which is 28 cross 28 pixels, which is 784 features. And my second layer is 182 dimensional. And then I'm defining my second FC layer, which whose input feature is 182, which is same as the previous one, and the output is 64. And finally, my FC is my fully connected 3-layer has input of 64. And since we have 10 classes for digits 0 to 9, we are sort of using 10 output layers. And as I discussed yesterday, forward is a method that sort of defines how this input will flow around this flow across these layers. So what we're doing is that we're getting the image X and we're sort of flattening it. So this step is flatten the input images. We're sort of flattening it to 784, and then we're passing to the fully connected one layer, the FC1 layer here, the first linear layer, and we're mounting it with ReLU layer, because we know that ReLU is a non-linearity, and ReLU is provides non-linearity, and we have to add it after every layer. Then you do the same thing for FC2, and finally we will pass the output to the FC3, which is our output layer and which has size as 10. I hope this is clear to everyone. Okay. So then loading the MNIST dataset. So yesterday we saw that to load a dataset, we have to load it using pandas.read CSV. So since the tabular data are in the CSV format, we need the .load CSV format functionality to load the tabular dataset. But since MNIST is an image data, we need additional functionality to load that. So, but if you see, all the standard image dataset is embedded inside Torch Vision. So we don't need to worry about how to download it and how to store it and how to reshape it. Everything else is done by Torch Vision. You just have to use that, and you just have to download that. So if you see here, Torch Vision has this block called dataset, and we can use the dataset module to refer the MNIST dataset .mnist, and we define the folder where we want to store the dataset, and also the transform. So if we do download equals to true, it will just download the dataset for the internet if it is not already there in your system. And if we do transform equals to transform, so we were defining a transform here. So when an image is there, it has to be converted to tensor at least, because we know that tensors are n-dimensional matrix, and it is easier to play around with tensor while working with PyTorch. So we also mentioned that yesterday. So we do this. We do that. We transform to tensor, and we also normalize it. Also, I also stated about the importance of normalization yesterday. So what I'll do is that I'll just take some blocks of code and put it in one cell and run it, so that you can get the clear idea. So that is for importing, and sorry, and this is for defining the network, and this is for loading the MNIST dataset. Okay, and since I've ran it already, so it has downloaded the code and kept it inside the data folder. See, there is a folder named MNIST, and inside of that, it's all encoded because it is reading by Torch Vision. You cannot see the images, but it is there. So then comes the part of data loading, data loader. So when we talk about MNIST, so we created the dataset here, and we store it inside our system. So the way we store CSV values or just tabular values is very much different with the way we store image values. So that's why images. So that's why we need a good data loader which can load those images from the computer and load it to sort of display it, or we can use that in our experiment. So we did that. So we defined some loaders. It is pretty straightforward and it is same for everything. So now we will do the training of the, now we'll do the training of our model. Yeah, now we'll do the training of our model. Let's say we are initializing our so for training we need to initialize our model, then we define the loss function just like yesterday, and we talked that for multi-class classification we use cross entropy loss, and we define our optimizer, and this is the training loop. And training loop is if you see, it is exactly same as the yesterday's loop, like this optimizer dot zero grad, then outputs equal to model, then you're passing images, then you're getting the loss, then you're back propagating the loss, and then you're they're performing optimizer dot step, which will just go and update the parameters. So if I just run this block, you can see the model will start training. It will take some time, but it will get trained soon. Yeah, you can see it is getting trained, and each epoch has an associated loss with it. Epoch 1 has loss of 0.3, and in epoch 2 the loss has reduced now to 0.18. So this will go on for 10 epochs, and 10 epochs is well enough to train this. And now you can see the amount of time it is taking for one epoch. If you remember, yesterday it was very fast. It was just like taking 10 seconds for 10 epochs. Now it is at least taking 1 minute for 10 epochs, because the network size has increased. The input layer yesterday has like 7 or 8 inputs, but now it has 784 inputs. So with increase of inputs, we're increasing the number of weights that we are training, and with the increasing number of weights that we are training, we are also increasing time to update and get the new weights. The A new and B news will take very long now. So that's why there is a time delay while training, and I, I guess it will be trained very fast now. Only 5 epochs are left. I guess all the epochs are done now. We can see you can go for the evaluation part to see the evaluation. Just give me one moment. I will reach back to you. Just 1 second. So now we'll evaluate the evaluation script, and if we run that, we can see we got a test accuracy of 97.19%, which is very good for this prediction job. So I'll just wait now and ask like if anyone is facing any issues while running this code on their system, please get back to me right now. Has everyone evaluated the code and got these results around 97.119? If you have done that, you can also say yes in the chat as well. Great. Now we will see how we can do this, how we can address the same problem with a convolutional neural network. Let's just import again all these things, and I'll be making blocks for it. So this will be CNN mnist CNN or mnist, and in the code block I'll be importing all those things. Let me name it as ANN for mnist. Yeah, and now we define our CNN. So in the CNN, if you recall, so let me go to this board and sort of draw a CNN, a sample CNN. So what I need to do is that I will. So here is my image of size 28. It's a 7 cross 28, and I need to apply the convolution operation here. So when I apply convolution operation, I need to define a filter with size, let's say K1 cross K1, and I need to define, let's say M such filters. And after that, I need to put a ReLU layer and yeah, and to put ReLU layer, and so this will, just 1 second. So this will give me a 3D sort of image whose size will be something L, and depth will be M. And we pass it to ReLU layer, and the dimension won't be changed. It will be same 3D image. And I will again pass this to a pooling layer, where in the pooling layer it will be like again get sorted as an image, and I will be repeating this. I will be doing a conv layer, a relu layer, and a pull layer till the point I get a small enough image, of course a 3D image, and which can be flattened to pass to a neural network. And we can use this to like we can use this to connect to other layers, and finally to the output layer of size 10. So now we'll learn how to code this in PyTorch. So in PyTorch, what we need to do is that we need to find um, in the PyTorch, we need to find this in the PyTorch we have this NN module, and in the NN module we have this conv 2D layers. So conv 2D is short for convolutional 2D layers, and this convolutional 2D layers has like this sort of thing. So here we define what is the input image channel number. So if you see here, the channel here is 1. The depth here is 1 because we just have a grayscale image. Then we define what is the number of filters we want to use. What is the number of kernels we want to use? That is 16. Then we define what is the size of kernel, which is 3. So here K1 cross K1, we defined here K1 is 3. Then we define padding. So remember we defined padding here, here. So they say that you can either add a layer of white patch around the image, or you can add 2 layers of that, like 2 white patch pixel layer. So now here we have considered only 1, padding goes to 1, and stride is by default 1, so we didn't mention that, but we assume that stride is 1. Then we defined a second convolutional layer where we kept the channel size to 16. So if you ask why, so here we see that we're using, let's say, 16 filters, and M is 16. So from these 16 filters, we'll be getting 16 2D images, and if we club that, we'll be getting 16 dimensional image. It's a 3D image with depth as 16. So this M will be 16. This will be 16. Sorry. So this M will be 16. M will be 16. So when you think about this, we can say that. So when you think about this, we can say that uh, the filter that we are going to use here in the second convolutional layer, these filters now. So if I denote filters here, these filters now will not be of 2D. It will be of 3D, because we have now 3D images, and as I mentioned here, for 3D images, we need to have 3D filters. Here, I mentioned here. For 3D images, we need to have 3D filters. So now you can see the input image had one channel, but now it has 16 channel. Now it has 16 channels. Now we again took 32 filters of 16 channel depth filters, and we kept the kernel size as 3 and padding as 1. We ended up having a different, like, second convolutional layer. And these are our two FC layers, which we will discuss later. But let's jump into the forward function that we have defined here. So we say that the input will now come from here, X, and if you can mark here, we flatten the input into 784, the flattening the input image. But if you see here, we haven't done any flattening operation here. We're directly passing it to the convolutional layer, because convolutional layer can handle 2D images, and we can pass it as a input image. By passing X to convolutional layer, we got the output, then we applied ReLU on top of it. The second step. The third step is the max pull step, as I defined here. Convolutional, ReLU, and pull. We did the max pull here. We did the max pull here, and after that, we applied the second round of conv, ReLU, and pull. So this is all done. We then flatten it. So you remember, for flattening, we just write x.view where -1, comma, and this dimensions number will do the work. So you see, flatten code for flatten is same as this line, is the same. So when you flatten it, then you just add another fully connected layer on top of it, just like here, and you add another ReLU layer on top of it. Finally, you add another fully connected layer, which output size is 10. And since its output size is 10, this is the output layer that we're working with. So now network definition is done. We can run this block to define the network. Then the standard loading the dataset and creating the data loaders is same as the previous time. So I'll just do it again. I'll not explain it. Okay. Then is the same as the past, the past run that we have done. It's just like taking the loading the images, then passing it to all these layers, and sort of getting the output, then creating the loss, backpropagating the loss, optimizing it, I mean taking a step, and then printing it, and this will do the training. I'll hit the training code now, and I would expect that everyone should do that, and it will take a while because we are using CNN. The network is bigger now, and it will take a while. Just you just hit run and wait to see the results. Done with 3 epochs. We're halfway through our training, and hopefully it will be done soon. The training is now done. We can do the evaluation now to see the evaluated the evaluation. And yeah, so you can see that there is a slight improvement in the accuracy. Earlier it was 97 point something, now it is 97.19, and now it is 98.97. There is a 1.5% improvement in this accuracy, and when the model is performing so well, there is no room for improvement for the second dedicated algorithm. So this ends our lectures about CNN and how to work with images. So there is a code block that is written for Cipher 10, and if you know Cipher 10, Cipher 10 is a colored image dataset whose images are of size 32 cross 32. I'll just show you the Cipher 10 dataset, and it is images of all these things: airplane, automobile, bird, cat, deer, and all these things. And so what you will do is that so you can run this code, and you can get the results out of it. So but this code is written in ANN. So the size of the image is 32 cross 32 cross 3, and if you flatten it directly to pass it to ANN, it will be 3072, which is huge, in numbers. And so it will take a lot of time to compute, but I will run it, and I'll tell you a trick how to use GPUs to make it a bit faster. Then I do not provide any code for this CNN for color images, and I highly recommend that to use CNN instead of NN for color images. But we'll discuss about these things, how to sort of create bigger models. So tomorrow sessions will be a bit more practical than theory. So I'll be covering a lot of practicals, and a lot of models will be trained tomorrow, so that you'll get a good grasp of all the concepts, and you'll know how to train a image classification model using a for colored images and for bigger images. The model that we train now today is very small and very very small little size, and very simple. But if we go about very complex images, it's very hard to train, and it will take time. So to run this, so all those things are same. You are importing something, then you are defining the network, then you are loading the data set, then you are creating the data loaders, then you are writing the training loop, and then you are evaluating it. One thing that changes here is this device. So here's a line. If you add this line to your code, what it will do is that it will check for CUDA. So CUDA cores are the GPU cores. If this CUDA cores is present in your system, it will use that. Otherwise, it will use CPU. CPU is slow, GPU is fast. And one more modification that you need is that whenever you are defining the model or defining the data set, you need to transfer those things into the CUDA. So I'll show you how to do that. So you see you're loading the data set here, just like MNIST, and you're defining the model here. And when you define model, you have to write this dot to device. So this will put your model in the GPU, and this images also, images to device and labels to device. So now you're training image, training labels, and the model is in GPU. And when you train this, so all the things, training and everything will be done in the GPU, and you'll now get a faster performance. So I'll take this block of code and put it out and see if the device is CPU or GPU. I'll just print the device now, and it is, you can see it is CPU. So to use GPU in Colab, so the one of the advantages of this using Colab is that you can use GPU for free for a limited amount of time. Of course, you cannot do very big tasks with it, but you can do simple tasks with it. But if you are using your local system, there's a possibility that there is no GPU in your local system, or the GPU that you have do not support CUDA, and you cannot use PyTorch GPU version in your local system. So to use GPU in your local PyTorch, what you have to do, you can Google this later as well. You have to go to the runtime. In the runtime, you have to go to this change runtime type. So you have to click on that. And when you see this runtime type, so the runtime type is Python 3, and there is hardware accelerator. And when you see this hardware accelerator, just choose GPU here. So when you change the runtime, it will restart the session. So you just have to hit OK. And GPU type here is asking. So here the GPU type is T4, which is free. But if you go for this faster GPUs, A100 and B100s, then you will be able to get access to that as well. Those are very fast. I think that comes with the price, but with T4 you will be fine. Then you just have to hit save, and you can see it will be using allocating. So it will allocate a GPU for you, and it will just take some time to allocate. So this is like the Collab Pro account, which you can get for faster computation, but as of now it will be fine. So it is now connected. Now you can run this cell and see. Okay, torch is not defined, so you have to import everything from scratch again. So I'll just run the first cell because the runtime is disconnected and started again. So I'll run it again and see. Now the device is changed to CUDA. Now if you run this block, all the Wi-Fi 10 training will be done in the GPU. So I'll just run this block and wait for the training to finish. And you can see the training will be much faster now. So it is downloading the dataset and it will be done online. No need to download any dataset to your local system. The training has started now. So one epoch is done. It is taking, so these are bigger images. This would be taking very long. But as with GPU, you can see it is very fast than just CPUs. And if you want, you can just disable the GPU and train it with CPU and see what is the time difference that you are getting for training in GPU as compared to CPU. So you can see the test accuracy is not that good. It's 51.99. So the reason is it's a colored images. It's a colored image, and it's a bigger image than the MNIST, and the spatial correlation matter. if I just flatten it out and train a model, this is not gonna work. This will take more time, as well as it will give worse performance. So I'll show you tomorrow how to improve on this test accuracy, and by building better and better CNN network, how can we improve this test accuracy from 51 to say 85, up to 85 we can increase. Yeah. So this is all about the CNNs, and I have shared the notebook with you, and I will share this OneNote as well, where you can find notes for all the lessons. Let me do that right away. And meanwhile, I would ask ma'am to conduct any quiz if she wants in the remaining time, or we can. For the time being, my session is done for today. And I'm sharing the notebook link here. Thank you.
Thank you, Subrat sir, for your patient session for your 3 hours. And I hope all the participants have enjoyed the session. And we'll end the session, and we'll post your quiz link on the WhatsApp group, and also the complete recording on your WhatsApp group. Okay. Thank you, sir. Thank you so much. Thank you all.
Thank you, everyone, for sitting and listening to the session. It's a long session, and we'll cover other practical approaches of the CNNs tomorrow. Thank you. I'm stopping the screen sharing, and I'm ending the session from my side. Thank you.